is something looking like this, and it's resting on the soil like so, and we're causing it to fail round like so. That's what we're thinking about. And we're applying a load plus the weight of this downwards. And what we want to know is, instead of the load we're applying to the soil, we want to know what pressure we can apply to the soil. So the pressure, remember we cut out from this unit length. So the area is going to be the width of the foundation times 1 in the other direction. And if you need to, write a B times 1 there, because it's the width of the foundation times 1 for unit length in the other direction.
Oh, the area of the foundation.
Yes, that's right.
What's the area of the circle?
No, we're trying to work out what pressure we can apply to the foundation soil, not what the shear stress is on the failure surface. Okay? Okay, as I said, when we move back to this slide, we are recapping because it's such an important point, but it does give you a chance to make any notes. For start, my typing is a lot neater than my handwriting. So what we've said was we might get tension cracks up here, replace a material which has strength and weight with a material that just has weight. So if there is any strength in this zone, because it will resist failure, it will help us, so it's safe to ignore it, but we also fear there are situations where it may actually be a good assumption. We come up with a failure mechanism like so, rotating round that direction. We've taken that diagram and converted it to a false diagram. So here we are here, and we've got Q bar, which is equal to the applied load plus the foundation weight. We've got the soil here replaced by its weight. And of course, we've got a normal stress all around that failure surface, but it always acts through the origin, not the origin, through the point of rotation. And we've got the shear stress there, which is, because it's undrained clay, is equal to Cu. And this allowed us to take moments where we got Q bar equals W soil plus 2 pi B Cu. There's actually there's a squared term missing there. Do apologise. The squared's got dropped out of the PowerPoint. So that should be 2 pi B squared Cu. Yeah, just like it was in your notes just now. And then we went on from that to say, when we converted that, yeah. Sorry, I've just realised I'm making life confusing. Having done it nice and clearly, of course, what I've done, there's 2 steps there. Because it's on the computer, I've done 2 steps, and that's why it isn't a squared. So, and then we got to that answer just there. I do apologise. That equation just there is the equation after we've multiplied through by b upon 2. And then that's the equation when we've multiplied through or divided through by area. OK. I want you to just take a look at that equation. What we got is the ultimate bearing pressure is equal to the surcharge pressure foundation level, i.e. the weight of the soil acting on foundation level, plus a number, 2 pi, times the strength Cu. So, I want to write it in this form here. All I've done is taken my 2 pi, and I've called it, because it's a number, I've called it a constant NC, the bearing capacity factor for the cohesion. And I've taken there, well, I've said I might want to have a constant in at that point there, times the surcharge pressure, but in our case, we got an answer of NQ equals 1. So I've written it in a notation. It's the notation you'll find in every single geotechnical textbook, but I haven't changed it at all. I'm saying, for the moment, that's 2 pi, and that's 1. OK, what did I say is the danger of this analysis? What's the danger? What have we done wrong? We ignore normal stresses, but they do act through the centre of rotation, so that's OK. But I said at the start, we're going to take a guess at the failure mechanism. And when you choose a failure mechanism, if you get it wrong, you can get the wrong answer. And not only do you get the wrong answer, but you can get an unsafe answer. And I also confessed, because I wanted to keep the geometry simple, because I wanted a geometry where the normal stress did act through the point of rotation, actually. That's one of the reasons I picked that. Well, the result is, I know I've got slightly the wrong mechanism. The right mechanism looks like this. And I've drawn it, by the way, I've drawn it, that's what we should look at there. Whenever you see us drawn in books, we always draw it going both ways. And this is because when you have a perfect soil, you don't know whether it's going to fail round to the left or fail round to the right. So both of them are drawn there. But what you can see there is instead of being a circular surface, there's a block of soil that drives vertically downwards or drives down on the incline when it starts to fail down this direction. There's a circular section of soil there. Unfortunately, for simplicity, if we want a simple answer, what's complicated about this is it's not a simple sliding block. It's a zone of shear deformation. And then we've got another simple block driving upwards. And if you study a bit of plasticity theory, it's not that difficult to perform an analysis on this. And if you were to do so, you'd find that you get an equation exactly in that shape, but we find that NC's 5.14 is actually equal to 2 plus pi rather than 2 times pi. You get 1 pi from this circular section here, and you get 2 from the 2 blocks, actually. That's why it's got a slightly different shape. So what we've found is we've got an equation with the right shape, but the constant we get is too high because we chose the wrong mechanism. It's about, I think it's 20% too high because 2 pi is 3.14, 6.28, and it should actually be 5.14. So we're about 20% high using our rather simple analysis. However, now we know that, that doesn't matter. What our simple analysis does is tells us what's going on, what is important. We're assuming a failure mechanism. We assume it passes through certain zones of the soil. We are idealising strength. We're idealising stiffness. All those things are true for both analyses. OK. I've picked an analysis for a soil where I've assumed that torr at failure, the shear stress at failure equals Cu, undrained soil. What happens? Just forgive me for a second, I just need to check something. Yep. I'm in the right place. So, we've got shear stress is equal to Cu. What about drain soil, where torr at failure equals, in the general sense, C dash plus sigma dash tan phi? Even allowing for the fact that that's usually small, the problem is not the C dash term, it's this term here. We need to know the normal stress on the failure surface. So our analysis took 4 lines when I did it properly. That analysis for that mechanism there takes about 2 pages. And when we get on to the torr at failure equals sigma dash tan phi analysis, it takes me about 5 or 6 pages of A4 to get through the proof. But the analysis is based on the same basic principles. Idealise the soil as rigid plastic, assume the foundation's rigid, and that a mechanism fails, and then analyse the limit equilibrium of that mechanism. So it's the same process. The mechanism gets more complicated, the equation for failure gets more complicated, but when we go on to drain soil, so now we've got our shear strength equation, which is generally C dash, torr at failure equals C dash plus sigma dash tan phi. What we find now is the mechanism is slightly different again. You still get, remember, it's drawn for symmetry because we don't know which way the mechanism is going to shear, but at the point of failure, it'll either go round this direction or it will go round that direction. It will be small non-uniformities in the soil being a natural material, which determine which way the failure mechanism will go. But what we have is, just as we did with the clay soil, we have a triangular block driving downwards. Previously it was a 60-degree triangle, equilateral triangle. Now it differs from a 60-degree triangle. The difference is actually related to phi. The bigger phi is, the more pointed that triangle becomes. Then, instead of a circular arc, we get a section, it's actually a section of a spiral. And it's actually a type of spiral called a log spiral. Now, a log spiral is a circle that opens out by a fixed amount through as they rotate round. So as you rotate round, it keeps opening out by a fixed amount. And it turns out the amount it opens out by is related to phi. So when you have a phi equals 0 soil, this defaults to a section of a circle. And then we get another triangle whose geometry is related to the phi value. So this can be seen, if you wish to, as a generalization of the mechanism for a clay soil, where with a clay soil, the geometry is fixed by phi equals 0, and here, the amount it opens out by, the amount of soil which gets involved in the eventual failure is dependent on the phi value. So it might be on a low phi soil just going around like so, and on a high phi soil it might come out right like so. But they're all part of the same family of mechanism. And you can perform an analysis on this. As I say, it takes many pages. It's a limit equilibrium analysis. It follows the same basic principles we've used. And what we find is we get an equation which looks like this. We still have, well, I put C there rather than CU because we're now dealing with C dash up there, aren't we? That's the surcharge pressure. We've dropped the 0 because in the standard form, this is exactly how it's reported in all textbooks. But that's the surcharge pressure.